passed through thermodynamics, we actually skipped something. There's something that we didn't mention when we were doing types of energy because it's basically built into the enthalpy of the system, and so we ended up not really needing to talk about the internal energy. But one of the components of enthalpy is something called internal energy. Enthalpy, which was H, was the sum of the internal energy and its pressure times its volume, and I gave it no definition during our thermodynamics unit. Because we hadn't talked about internal energy and because we hadn't talked about gases, we couldn't talk about internal energy. So now we have to kind of go back and give it a definition. Essentially, enthalpy is the amount of energy needed to bring something into existence plus make room for it in the atmosphere. If something comes into existence, the atmosphere has to get pushed back to make room for whatever it is that just came into existence. The internal energy, some textbooks go with U, some textbooks go with E, is the sum of the molecular level kinetic and potential energy of the system. It's the energy needed to bring the system into existence in the absence of changes in temperature and volume. It consists of two pieces, the motion of the molecule and the attractive forces between molecules and molecules, between electrons and protons, between nuclear particles, and so on and so forth. So imagine having to account for absolutely everything in the system that's moving, down to the electrons, and having to account for every attractive force in the system. Chemical bonds, intermolecular forces, electrons to protons attraction, strong nuclear forces. If you could account for all of those things, that's the internal energy of the system. This and this are impossible to measure. I mean, the task is just too daunting. So what we settle for is to measure changes in enthalpy, delta H and delta U. And delta H is the change in the internal energy plus the current pressure times the change in volume. Essentially, as it has to push back the atmosphere to make room for it to exist, how much volume does the system actually have to occupy? We have learned about delta H. It's the one that chemists actually use most often. I don't think ever, aside from having to teach thermodynamics, that I've ever had to use internal energy. And that's why I focused so much on delta H coming through before. Changes in internal energy are actually a result of two different processes, heating and working. By the first law of thermodynamics, delta U of the system and delta U of the surroundings has to be zero. It's the conservation of energy idea. But it doesn't really prove to be very useful because measuring delta U for the surroundings is an impossible task. So this isn't a remarkably useful version of law of conservation of energy. The system, however, only has two ways of exchanging energy with the surroundings. We're familiar with one of them, heating. We gave it the symbol Q. Heating is an exchange of energy that results in a change of temperature or a change of physical state. We had a couple of equations to account for that. Working is the new one today. Working causes a change in volume. The amount of working done is the opposite of the pressure, because the pressure is what you have to work against, times the change in volume. Therefore, the change in internal energy is the sum total of all the heating plus all the working. I kind of like this little picture as a representation of this. The system can essentially exchange energy in two ways. Heating can bring energy in. Heating can allow energy to flow out. So in any given process, it's either endothermic, energy is flowing in, or exothermic, energy is exiting or flowing out. This piece we're already familiar with. This piece over here, we're not as familiar with yet. If working is done on the system, the surroundings is squeezing the system and essentially giving it more internal energy. Imagine like taking a balloon and squishing it in. You're giving it energy because as soon as you let go, it's going to go poof, and go back to its normal size again. Working is done by the system if the system has to push the environment back in order to make room for itself. So working is thought of as working on the system by the surroundings or working by the system onto the surroundings. The system is nothing more than the part of the universe that we're trying to think about here, and the surroundings goes into the category of everything else. So sometimes we say that when the system has to push back the atmosphere, that the work is done by the system, or in other words, the system does work on the surroundings. When the system no longer needs as much space and it shrinks back up, the surroundings does work on the system and the system is going to shrink. Sometimes we say that the surroundings does work on the system. You can see there's two ways that the system moves energy to and from the surroundings: Q out and Q by, or exothermic and expansion. There are two ways that it could gain energy: Q in and work on, or in other words, endothermic processes or contraction. Now, to kind of help you see this, I'm going to use one of our Whack-A-Pack balloons. Because the Whack-A-Pack balloon is something that has to do work on the surroundings. It's easiest to think about working if you imagine putting your system into a balloon, because then you can really see when the atmosphere has to be removed. Now, I'm going to take the balloon out of its package here so we can actually see the balloon. So, Happy Easter. Okay, it's a little late for Happy Easter, but here's our balloon. Nice and flat. Our system isn't taking up very much space right now. When I do this and start the chemical reaction, our balloon is expanding. The thing that you tend not to think about is that in order to expand, the balloon is having to push back the atmosphere to make room for itself to get fatter and fatter and fatter. Working is the process of pushing the atmosphere back and out of the way. And if you just think about pushing as something that involves some amount of working, you've really got the idea of working. Okay, so the balloon expanded, it had to push back the atmosphere and make room. Because we're pushing back the atmosphere and the volume is increasing, the quantity negative P delta V is going to be negative, so working is done by the balloon. The balloon is having to spend energy to push back the atmosphere out of its way. That's about the idea of working here. Okay. So we're going to kind of take turns. I'm going to work some examples, then I'm going to give you a chance to have your turn, and then we'll go from there. Okay, I think girls track. Now you get to leave. Okay. Calculating work done on or by the system. All right, so bringing forward from the other page, working is the opposite of pressure times the volume. We want to calculate the work done by the gas if it expands against a pressure of 1.2 atmospheres. So the first thing to think about is by how much did the volume change? Like all changes, it's a final minus initial, and that's important because it's going to get you your positive or negative sign. So we went from 2 liters to 6 liters. 6 liters minus 2 liters. Our volume has increased by 4 liters. To calculate the working done here, negative 1.2 atmospheres times 4 liters ends up being a negative 4.8 atmospheres, or liters times atmospheres. Which means that our system is essentially spending energy. It's spending energy to push the atmosphere back and out of its way. Now, this liters times atmospheres set of units isn't going to be remarkably useful because working's partner is heating, and heating carries energy of joules. So we don't want to have to add these two things together and have them in different unit systems. So one of the things on your resource sheet this time around, right next to the working formula, working is the opposite of pressure times the change in volume, and 1 liter atmosphere is 101.3 joules. Aha, we can get ourselves to joules. One liter atmosphere is equal to 101.3 joules, or negative 490 joules. Now, the actual meaning of this is that the gas is expanding. So the gas does the work and an energy asset, that energy asset being working, leaves the system thus working is negative. It costs energy in order to expand. That's what we are learning from this entire experience. Expansion is not free. Expansion involves the expenditure of energy to get the atmosphere out of your way. Unless you're doing this in a vacuum. If you're expanding in a vacuum, there's nothing to push against. If it takes place in a vacuum, working is 0 atmospheres times the 4 liters by which the system expands, or 0 liter atmospheres, which is no energy spent. So if the classroom had been a vacuum and the Whack-A-Pack balloon had needed to expand, the Whack-A-Pack balloon would not have had to spend any working assets because there would have been nothing to push back and out of the way. Okay, your turn. Try that one.
You hold your pencils weird. It's like an insecurity that I should not